Well, greetings, everyone. My name is Adam Hams, and you are watching or attending, for those of you live tonight, welcome, the March 2022 edition of the Houston Azure User Group. Still virtual, but maybe one of the last few, if ever, I think, that we all need to have. So I'm the leader of this group. I've been leading this since 2015. And we've been trying to meet pretty much every month for Houston-related topics. And for those of you new to the group, the purpose of our group is very much community. So this is an opportunity to learn from one another and from the speakers. It's not a sales pitch. If you're here for a sales pitch or looking to sell to the other folks in the members of the community, in the wrong place. But if you're here to learn, absolutely the right place. Learn from others or share your experiences of using the various Azure technologies, the journey that is cloud, looking to share those experiences with others, then this is the right place. And there's quite a lot of experience to go around now. When we started in 2015, Azure was a mere 5 years old. So it was just starting to mature in 2015 with a set of capabilities, role-based access control. What is now the classic technologies were starting to be replaced. So we have a slew of features now in the 7 years since. So it is truly a colossal monster. So it has been fun to see that journey. I myself, my day job is as a cloud architect currently with Microsoft. Microsoft for 15 years, based in Houston. In fact, Katie, we were talking about this earlier in like the pre-chat. So I'm in Katie, and many of you I think are in Houston. A warm welcome, but because we're virtual, not necessarily all in Houston. So for those of you not in Houston, a warm welcome. Great to have you with us. Let's see. So without further ado, our speaker tonight, Jordan, reprising his role. So this is your second time, I believe, Jordan, right? You were in person the first time.
I think it's 3 times.
Oh, was it the third time? I'm missing one.
Third time, yeah.
Yeah, third time. Excellent. We're very fortunate to have you. Without further ado, please start teaching us your content.
Okay. Oops, wrong screen. Let's try that again.
And I should add, actually, while you get set up there, start presenting, we have mics open if you want to jump in with questions, or the chat. I shall be monitoring the chat and answer questions on that. So or jump in with your mic if you wish. All right. Thanks, Jordan. Go ahead.
Okay, can you see my screen?
Sure can. We're all good.
And you can hear me.
I can indeed, and
all right,
see you.
Fantastic. So that
it is.
We got all 3 today.
All the technology is working.
Cool.
It's a beautiful
nice.
thing.
Awesome. Okay. So howdy, everyone. My name is Jordan Bean. I am a senior cloud solution architect in what's called app innovation, which for Microsoft means anything software development related. Specifically, I'm assigned to U.S. manufacturing companies. I'm based in the Houston area. And so today I want to share with you an application and an architecture that I built for a customer that I'll call orchestration and event-based autoscaling using Azure Durable Functions and KEDA on Azure Kubernetes Service, or AKS. And like Adam said, please feel free to interrupt at any time with questions or put them in the chat, and Adam or Terrence or myself can answer those questions, or we can answer them afterwards. All the slides can be shared. There's nothing proprietary or secret here, and all of the code will be available on GitHub, so you can feel free to take it and use it to build whatever you want to build. So the purpose of the session today is to talk about the functionality and benefits of durable functions for orchestration and KEDA on AKS for autoscaling, and to demonstrate the use of those 2 technologies with a demo application. So let's talk about the business problem. Let's talk about why I was asked to help with this. So I was talking to one of my customers, and they said, hey, Jordan, we got this Python application that one of our data scientists wrote. It's really complicated. It adds a lot of value to our business. It's really complicated. It's multivariate, meaning there's lots of different input data into this Python simulation engine. And the whole idea of it is that the Python simulation can explore an entire problem space. You input some low-end data, some high-end data, so you've got the whole range, and you have it auto-generate a bunch of scenarios You simulate all those scenarios, and then you look at the results, you score them, you decide what you want to do next, and you do another iteration of the simulation. That's what they had built. They had a PhD that had built this application in Python. They wanted to move it to Azure. They wanted to take advantage of some Azure technologies to make it work better. So that's what they came in, and that's what they asked me for. This is a very stereotypical kind of data science-y workflow and ask. So they wanted to see how could Azure make this better. If we simplify it just a little bit, this is the idea of what they wanted. They started off and they had a whole bunch of scenarios that needed to be generated. Remember, there's a low end and a high end of all the different multivariates that they wanted to generate simulations for, and they had written code to do this already. Those simulations could all run in parallel. Each one was completely independent. They could all run in parallel, fan out, use as much compute as was necessary to process, to generate the simulations, to score them. They wanted to aggregate those results. And then they wanted to look at those results and decide what they wanted to do next. Very likely they would change some of the input data, regenerate simulations, and run again. It's a very batchy process, a fan-out process, very stereotypical. They wanted to use Azure to make this better. They wanted more compute. So the first answer to what they're doing is Azure Durable Functions. There's a couple of different orchestration systems that you could use in Azure, like Logic Apps. There's some HPC systems, but Azure Durable Functions are a very simple and easy way to have an orchestrator where you don't have to write the code yourself for things like, I want to start a job. I want to keep track of jobs. If a job fails because of a compute problem, I want to run it again. So durable functions already do this. They can do what are called stateful functions in the serverless compute environment. They already have capability to fan out and fan in, aggregate results, check to see is a job done, and tell you when all the jobs are done. It manages all that state, all the checkpoints, the restarts. Azure Durable Functions does all this for you. Logic Apps have a similar functionality, but in this case, this customer wanted a lot more control over defining all the simulations in the fan out than Logic Apps would give them. And so Durable Functions is a pre-built Azure service that already can do that kind of job scheduling service for you. So you don't have to write code to do that, and you don't have to buy code to do that. From some other place, Azure Durable Functions already do that. So it's a perfect service for them to build the orchestrator. And just like we saw in the previous example, the orchestration engine kicks off. It fires off a whole bunch of activities. All those activities run in parallel. Each one computes one of the simulation inputs. They write their data to a results location, and then you can iterate on it. So durable functions fit perfectly with that fan-out style of simulation that these users were looking for and that this compute was looking for. Are there any questions so far about durable functions or how they work? No? Okay. So what happened is they built their orchestrator to generate the simulation data. And they had broken up those simulation steps into a few smaller workflow steps to try to get more fan out, to get more scaling out of the Azure functions that they were using. So they had a small workload, generate multiple activities and execute them. Those activities would fan out and call other activities, worked really, really well for small workloads. Oh, but then it failed. Ultimately, the real logic of the application, the Python scoring engine, was this massive monolithic Python module that they had written. And yeah, maybe if they had rewritten the whole application, they probably could have gotten a little more scale out of it or a little bit better into Azure Functions, but they didn't really want to. They felt that this monolith kind of fit with their process. They didn't want to rewrite it. Ultimately, what they wanted was the fan-out procedure. They wanted to keep it the way it was, but Azure Functions really didn't fit for that huge workload that they were looking for. It wasn't enough compute power. It wasn't enough cowbell for what they really wanted. They needed a different compute engine in Azure. And so that's what we worked together to build. So just like everybody else, they want to scale up and they want to scale out. They needed more CPU, more memory, more GPU for that heavy duty Python computation engine than they could get out of the out of the Azure Functions. And they want to scale out. They really liked that ability of Azure Functions to scale out to lots and lots and lots of compute on demand, but Azure Functions really couldn't scale up. It couldn't give them the GPU they needed. It couldn't give them enough CPU and RAM for what that Python module wanted to do. So they needed a different compute engine. So what could we do to make it so that they could host in a different compute engine that Azure has available? So in order to do that, we've got to structure their application in a very specific way. So at the core of it is their Python business logic. This is the moneymaker. This is what the PhD was paid for to make. This is their data science engine. This is the compute engine. This is where the money is. This Python business logic needed to be very tight and focused on the algorithm that they wanted solved. It didn't need to know anything about Azure or running in some other compute environment, whether it was local or anywhere else. It needed to take some input data as arrays of doubles and ints, simulate it, and then produce some doubles and ints as its output. And that's what the Python business logic needed to stay as. It didn't need to know anything about Azure. And so we pulled out anything in it that was not about the computation. That way, when they were working on that logic, it could run on their local computer. They were trying it in Azure Functions. That wasn't good enough. We'll pick a different compute engine in just a minute. But that's the idea. The Python business logic, very tightly focused on the business problem, not anything about the hosting environment. Once we had that, we needed to write a wrapper. We wrote a little Python wrapper around that business logic. The wrapper is what knows about Azure. It's what knows about getting some input data from some source, writing some output data to some other source, and dealing with the orchestration, dealing with the hosting environment. We need to abstract that away from the business logic so that the PhD never sees it, never knows about it, doesn't care. So this Python wrapper is where we're going to hide all that input and output. Once we've got the Python wrapper, we can Dockerize it. Once we've got a Docker container, we got a lot of hosting options in Azure we could choose to run this application. And it doesn't need to know anything about it. It just runs as a Docker container. And the Docker orchestration environment doesn't know anything about our Python wrapper or our business logic or anything else. It just runs a Docker container. Easy to spin up, easy to spin down. So Azure has a lot of compute options. There's actually more options than even this for hosting containers, but these are the stereotypical ones, the one you see the most. Of course, you could run a container on a Linux virtual machine. Totally works. But you really don't get a lot of scale out of that, and it's really not the right environment. It's overkill. Azure Batch can do this, and that was an option that they seriously considered because Azure Batch can run containers, and they liked the whole HPC aspect of it and the PBS job scheduling part of it. That's an option. Some people may have chosen that one. App Service is the next option. App Service is really good if you want to run one container. If you have a big monolithic application that you've written, it needs to be deployed as a container, but you're not going to do any orchestration. You're not really going to scale it up or down all that often. It doesn't really need to have that complicated communication with other services. It's one monolith. App Service is great for that. But that didn't really fit their use case either. So then we picked some others. We have Azure Container Instance. Container Instance has been around for a long time. If you need just a few containers, Container Instance is a great option for that. You'll see this a lot in batch processing and machine learning using Azure ML Studio. You'll see Container Instance show up a lot as a way to have that compute on demand. You could even use Container Instance as a virtual node pool inside AKS and use it for extra compute on demand. But Container Instance doesn't give you a lot of control over the SKU that actually runs your code. It's more logical. It's meant to say, I want one CPU, I want 8 gigs of RAM, and maybe I want one GPU, but it's all logical. You can't really say exactly what you want. And in this case, the customer really knew, based on the way the Python was written, what SKUs in Azure were really interesting to them and what would run their code effectively. So Container Instance didn't really fit. Azure Container Apps is a new service. It's technically not even GA yet. It's still in preview. But it would probably be a great environment to solve this problem where you want to scale up, but you don't really want to deal with all the orchestration complexity that Kubernetes has, but it wasn't a GA service, so they weren't ready for it. So finally, in the end, we picked Azure Kubernetes Service. It's the big hammer. It can do anything related to containers. It can scale as big as you want to go, but it is the big hammer. It's the most complicated option, it's the most expensive option. But for them, they needed it because they wanted to pick the SKU that they wanted to run their containers on. So you can pick via the node pool in Kubernetes service, and they wanted that massive scaling capabilities that Kubernetes can offer. So in the end, even though it was expensive and more complicated than the other options, that was the option that was best for what they wanted to do. And there are some other options in Azure, but this is what they chose. All right, so now we've got some compute engines, we've got some durable functions. How do we scale out? in Kubernetes. How does that work? So we're on the right-hand side. We have Azure Kubernetes Service that runs our application. It's running inside a Kubernetes pod. We've got our Docker container with our Python code running in it. So we've got one compute engine running to process our data. We need a place to put that data. We need a way to tell the Kubernetes pod, hey, here's some data I want you to process. We want it to be very event-based. There's nothing to process, don't do anything. But if we start putting things on a queue, we want that queue to be processed. And there's a couple different queuing technologies in Azure, like Service Bus and Event Hub. Ultimately, they chose Azure Storage Queue as the option they wanted, but there's several. So Azure Storage Queue, we're going to put some data on the queue. Our Kubernetes pod is going to see that data and start processing it. And we're going to start getting more data, faster and faster and faster. And what we found was, by default, the horizontal autoscaler that's built into Kubernetes that decides how many pods you should have running, it wasn't really scaling well for this use case. Because ultimately, the horizontal autoscaler that's built into Kubernetes, it really only observes things like the CPU utilization or the memory utilization of the container. It can't really see outside of Kubernetes to see how much work there is and how much to scale up or down. We needed something that could monitor outside of Kubernetes because we know via the storage queue how many items there are to process. And so we need a service that can monitor the storage queue and tell Kubernetes to scale up or scale down as needed.
Hey,
And that's
John,
where KEDA.
real quick. So could you just clarify what is a pod? What is a pod,
Absolutely.
please?
So in Kubernetes, no matter whether you're doing AKS or any other environment, a pod is a way to run one or many containers. It's ultimately the logical wrapper that goes around a Docker container or a few Docker containers. It's meant to be one logical compute unit, and then you scale up or down by adding more pods, each of which is an identical copy of the previous one, just like you would make multiple virtual machines with the exact same code running on them. That's what a Kubernetes pod is. It's one or many Docker containers that is the logical compute, one logical compute device for whatever your code does. So if you're running like a web server, you have one web service, you have one pod running, and if you needed to scale up because you had more traffic coming in, you'd make another pod, which would have your two web servers running in it to handle all your traffic. So pods are the way that Kubernetes scales up and down its compute. Okay.
Thanks, John.
All right, very good. Okay, so how do we get the scaling? How do we tell Kubernetes, hey, there's this thing outside of you that I want you to monitor? The solution to that is a program called KEDA. KEDA stands for the Kubernetes-based event-driven autoscaler. This is not Microsoft specific. This is an open source project. This is a service that you can install on any Kubernetes cluster you've got, whether it's AKS or one of the other places that you could run Kubernetes. And it gives us exactly what we wanted. It scales containers based on the number of events in some external system that we tell it to monitor. And it integrates with a huge number of external sources. And very importantly, it can scale all the way down to 0 if needed. And this was really important for this customer because they were very interested in this idea of they're going to run a bunch of simulations and then they're going to analyze the results for a few hours. And so they didn't want to spend money on compute if they weren't actually computing anything. They didn't want a whole bunch of compute running with nothing to do. They wanted it to scale down to 0 until they were ready to generate more simulations. And so that's what KEDA gives them. KEDA allows you to scale down to 0 and up to as high as you want to go. KEDA, again, is an open source project, and it has a huge number of what are called scalers. The scalers are the thing that listens to some external environment. And you can see there's a huge number of here. Obviously, it's got great integration with Azure. It can listen to blob storage or event hubs or log analytics or Azure Monitor. It can listen to pipelines. It can do the things that the horizontal autoscaler inside Kubernetes can do, like CPU utilization or memory utilization. It could listen to those other cloud environments and things that are running in them if you so choose. It can listen to a SQL Server database table. It can say, hey, if I ever insert a row into this table, go do something. There's a whole bunch of choices in what KEDA can listen to decide how to scale. Obviously, in our case, we already have a storage queue, and that's what we wanted KEDA to monitor and then scale up or down as needed. And so that's what we chose. So again, what KEDA is a service that runs inside your Kubernetes cluster. And you point it at some external source, some place that is making events, some scaler, in our case, Azure Storage Queues, and then it will decide how many pods are needed, how much compute is necessary based on the configuration options that you give it when you set it up. So that's how KEDA works. Instead of me writing all the complicated logic to figure out how high should I scale or when should I cool down, how often should I poll, all that logic that I would have had to write myself, KEDA's already done and done better than I'm going to do. So KEDA is a service, a scaled object that you deploy inside your Kubernetes cluster, and you need to give it some configuration information. The first thing we give it is up at the top, the scale target ref. That's saying, what is the thing I want to scale inside Kubernetes? In our case, a deployment. A deployment is a logical number of pods that you would like. And so we want to scale our compute based on some external factor. So that's what we tell Kubernetes to scale. We have things like polling interval. How often should it check that external queue to see, is there anything new to do? How often, or what is the cooldown period before it decides to scale up or down? What is the minimum replica count? How few containers can possibly be running? In our case, we wanted 0. What is the max? How many maximum containers do we want to save money and to save compute inside our Kubernetes cluster so that it didn't overwhelm the system? Whoops. We said scale up to 100, but you could do 1,000 or whatever makes sense. And then you've got a trigger. The trigger says, hey, what is the thing external to me that I'm monitoring? In our case, it's an Azure Storage Queue. And we give it the name and we say, hey, if more than 5 items show up in that queue, start scaling. So it's going to start scaling up. And if we get to less than 5, it'll start scaling down. And it does all the complicated logic for us. It figures out how to scale. I don't have to write any code to do it. Just give it a little configuration, give it the thing I want to scale, which is my Python business logic, and it goes and scales all by itself. Very exciting, very easy to use, already built in, ready to go. And excitingly, in container apps, the service that I was telling you about that's not GA yet, KEDA is a built-in scaling option. So you'll be able to do the same thing in container apps once they become GA, hopefully in the next few months. So let's watch the scale out happen because it gave us exactly the behavior we wanted. So we've got Kubernetes running, we've got KEDA autoscaling running, and we've got a storage queue. There's nothing in it. We put some items in it. KEDA is going to see there's some work to do, and it's going to give us a Kubernetes pod. We've got one instance of our Python business logic running. But now that durable function, remember the orchestrator that's generating all those simulations, it's starting to add more data to process. There's now 2 items to process. Now there's 3. KEDA starts to realize, hey, I'm not processing the data fast enough. Work's coming in faster than my one pod is able to process. And so KEDA starts scaling up. Now I've got 2 pods to process, but I've got 4 work items. Now I've got 4 Kubernetes pods. I've got 6 work items. It's processing as fast as it can, and KEDA is going to keep scaling up to the limits that we gave it to scale. And just like we asked for, it also scales back in. So we've got a bunch of items in our storage queue. As they start getting processed, KEDA will realize, hey, now I'm processing the results faster than they're coming in, so I don't need to have so many items running. I can start to scale down again. So as the work items start to disappear, KEDA keeps shutting down pods to save me money, and eventually nothing's left. Kubernetes is running, KEDA's running on it, but my expensive compute engine that's running on these really expensive SKUs that have GPUs and a lot of RAM and a lot of CPU available, they're not spending money anymore. They've been shut down. So this very batch style of process was what they wanted. They wanted that event-driven auto-scaling, and that's what they get with KEDA, storage queues, and Kubernetes. So we've got all the pieces of the puzzle.
Does each Azure storage queue item represent one simulation or one job to run?
Yes. Yep.
And can they only run on one of these pods at one time? Does it have for example, in Azure Functions, there are 2 concepts of scaling. One is number of instances of app service or the underlying virtual machines workers. And then there's also the batch size, where each worker's run method can technically process up to the batch size number of items in the queue, for example, at the same time. So in this infrastructure, each of these pod that you have, does it only process one job at a time, or does it actually process multiple jobs simultaneously?
So that's configurable, but you've got to write that yourself. It doesn't have that built-in batching, but I'll show you the code in a little bit and show you where you could do batching if you wanted to. And if it made sense, you could.
Gotcha. And I had an earlier question in the chat. Can you give us a brief idea on how intensive this job is? Like, because we know it can be very complex and very intensive, but let's say in a typical computer, was it taking how long to run, in hours or minutes, and how much RAM and CPU power is generally used? And just, layman's term.
Right. So for this customer, the simulation job could vary in general, it was on the order of minutes, but as they continued to add in more multivariates, they started to see that Azure Functions was taking longer and longer, and it was getting to take hours, and that was kind of exceeding some of the timeouts that are built into Azure Functions. And ultimately, waiting hours to have it all run wasn't good enough, and that's why they wanted to be really specific on the SKUs that they could pick. Where with Kubernetes, you define a node pool. And so you say, I want a Azure VM with this many CPUs, this much RAM, this speed of CPU, this many GPUs, and whatever, so that you can be really specific. And based on their testing on their local machines, they had a good idea of exactly how much CPU, how much RAM, and how much GPU was really needed to be allocated to each one of the compute engines.
The other thing that I want to see if you can address is why did they not consider parallel processing architecture? I mean, Python is notoriously slow. We know the GIL, it serializes everything. There are better languages / systems out there.
Yes.
To create parallel processing environment much better, and Azure has those. So I'm kind of curious.
Yes, absolutely. That was one of the first things we talked about with them was, hey, you could rewrite this in C++ or in C# or in numerous other languages that parallelize better than Python does for exactly the reasons you said, like the GIL. Ultimately, for them, it was more important that the data scientist be able to write the code, change the code, and understand what was happening. And they can throw more hardware at the problem by hosting it in Azure. If they had been very compute limited and they hadn't had all these different services that we can run in Azure, they might have ended up going down that path of the data scientist writes it once in Python, but then it has to be handed off to a programmer who can write it in C++ or C# or some other language that gives that better parallel processing. But they didn't really want that. They wanted the data scientist to really be able to own all the code for the compute engine and change it as they continued to learn and realize what was needed to solve their business problem and throw more hardware at it. And Azure obviously has a lot of better compute options than they could do when they ran it on-prem. That was their reasoning for doing it. They could have chosen something different, but that's what they chose to do.
Now, you're saying that container apps could be an alternative for them instead of Kubernetes services. Do you know that container apps give you the opportunity to select the cluster type, CPU type, as AKS does? I don't know.
That I don't know yet. I've only played with the preview a few times. I don't know how much choice you have in the SKUs. So it might not have been the right choice. I don't know.
Yeah. Not a lot. It's a parse. So yeah, you don't get to see that with container apps. That's one of the things that's effectively hidden from you, the SKU choice. Currently.
Okay. Any other questions? No? Okay. So this was the overall architecture that we built for them, showed them how to work, and they built themselves. So just like we talked about, we have an Azure durable function set up. So they had a web app that they had written to help the data scientists come up with the simulations, and it would call a REST API endpoint, the Azure function that's sitting out there. The orchestrator will go and fan out and start creating a whole bunch of little Azure functions that start to generate all that simulation input data, because it was on the order of tens to hundreds of megabytes big, the simulation input data. And so we ended up splitting it. So the simulation input data got written to blob storage as a JSON file. But the path to the simulation job data was put on the storage queue. So we would write JSON file 1, and then a path to JSON file 1 in the storage queue to indicate that there's one file that needs to be processed, and then write file 2 and file 3 and file 4 and so on. Because the storage queue is not meant for large entities, it's meant for very small amounts of data, and then in blob storage, we can put in those very large megabyte or gigabyte sized input data files that they were generating. We split it into two. Now we have our Kubernetes service with KEDA. It's listening to the storage queue, and it realizes, hey, now there's some work to do. The Azure Functions have started to insert rows into my storage queue. I have something to do. So it starts creating those compute pods. Those compute pods via the storage queue entry now have a path to blob storage to say, hey, here's the input data for job 1. So they grab the data for input 1, they process it, they compute it, and they write that data back out as another JSON file to another blob storage container. Remember that Python wrapper we talked about? This was very important that their business logic didn't know anything about Azure. All it knew was take some arrays, generate some arrays. The wrapper is the one that knows, oh, I need to write some data to storage. I need to read some data from storage. The wrapper is what deals with that. And KEDA will scale up and down based on how much data or how many entries are in the storage queue. We can use event grid every single time that storage container gets written to. Job 1 is now complete. A little Azure function can fire to report back to the orchestrator to say, hey, I'm done with job 1. Hey, I'm done with job 2, all the way until it's done. Then finally, the orchestrator knows how many simulation jobs were spun up, and it can report back to the user saying, hey, I'm done with all simulation jobs. Now you can go evaluate the results. And likewise, you could have interrogated the orchestrator during the job and provided some preview data or say some status saying I'm like done with 5 jobs out of 20 or whatever the requirement was. And again, you don't have to build any of that yourself. Azure Durable Functions already have all that logic and all the status updates and the restarts in case any of these Azure functions crashed. It would already go and restart them. And likewise, if our Kubernetes cluster crashed or one of our pods crashed because something happened, the storage queue is durable, meaning Kubernetes, my pod, is going to try to pull one entry off the storage queue and process it. But after it's done, it's got to report back to the storage queue saying, hey, I'm done. Otherwise, the storage queue is going to put that entry back on its queue, and another pod would have to pick it up. So durable functions on the left-hand side ensure that all the simulation jobs get kicked off. But on the right-hand side, the storage queue ensures that each message gets processed exactly once. So I don't have to write any logic to do that. Those are already things that are built into the services. So that's why we picked those services. Okay, are there any other questions about that before you see a demo?
You know, this is a really cool architecture, very nicely done.
Cool.
Let's see the demo.
All right, cool, awesome. So let's start up a demo and let's see it happen. Okay, so to make this easier to understand, I wrote a little web app to monitor what's happening. So we can see we've already got a node pool running with our VMs, because that's what a node pool ultimately runs on, is some VMs that they pick the SKU for that has some really expensive compute running on it. They're already scaled up for the purposes of the demo, because otherwise it would take some time to scale up and we'd have to sit here and watch. There's no messages sitting on the queue currently, and there's no pods with my compute engine running. And, you know, just in case you don't believe me, we can interrogate that. There's no pods running in my compute namespace for my AKS cluster. Sitting there, there's nothing going on. It's just waiting for some work to do. Okay, so remember, Azure Durable Functions are an Azure function, meaning they expose a REST API endpoint all the time. It's always sitting there. I'm going to call the orchestrator and say, hey, please generate 100 input data. Please generate 100 simulation jobs. That's what we're going to do. So this is what, in their case, they had written a front-end application for their users to use that would generate this input data. We'll kick this off. Okay, so what's happening in the background? My Azure Durable Function Orchestrator is starting, and it's starting to fan out, creating all those little activity functions which start writing data into storage and onto the storage queue. And now we can see messages are starting to pop up in my Azure storage queue. There, it's starting to get in there faster than it's being processed. Remember, I wanted 5 items or less in the queue. So KEDA is now going to start spinning up more pods. So now I've got 4 pods running. And if we go look, we can see those. You can see it's running containers and it's standing up more because KEDA is realizing that messages are coming in faster than they're being processed. So KEDA is going to continue to scale the cluster. It's going to start adding more and more and more compute to try to bring this number down. Eventually, my Azure Functions will quit, meaning they've written all the simulation input data necessary. My pods are continuing to process it, and the storage queue is starting to decrement as we run out of work to do. But KEDA is going to keep trying to make sure that I'm processing that data as quickly as possible. So we're starting to run out of work to do. 14 pods is enough to process all this data. Nearly done with all the work, at least on the input side. And now we're done. Okay, so all the data has now been written. It's all been kicked off. KEDA has now, or pardon me, my compute engine's run. It's processed all the data off the queue. And now KEDA is going to say, hey, there's nothing left in the message queue. There's no more work. I need to scale back down. I need to stop wasting money. So KEDA is going to eventually realize that there's nothing left to do, and it'll start to scale down the number of pods. And so that's what you'll see in just a second. And there we go. If we go back and interrogate my cluster, it's already shut down all the pods. And my web app will update in just a second saying there's no pods left running. Okay. All right. So where's the magic? How did that happen? How did I do all that? So let's go through it step by step. Look at all the code. There's nothing secret or proprietary here except my algorithm. Don't steal my algorithm. It's really, really complicated. There's a lot of money here. Don't steal my algorithm. I've got a compute algorithm. We'll take some input data. Oh, maybe my compute isn't so complicated. I'm going to sum up that input data and return it. You know, you got to protect the innocent here, and I can, you know, do some work in the future to speed this up over time. Okay, so the whole point of this is we wanted to make it so that the business logic that the data scientist was writing was very algorithmically focused. All the data scientist has to know, you're going to get an input array or a NumPy array or whatever was appropriate. In this case, it's just an array. Write your mathematical algorithm, write as many functions as are needed to do it, and then return an array or several arrays. That's all you have to know. The data scientist doesn't know anything about Azure. They don't need to know it. They don't need to know anything about the hosting environment this is going to happen in. They can be very focused on writing an algorithm. And that's really what we wanted, what we wanted to optimize for.
Jordan, a quick question. Does this depend on how the sum, parallel the operation? If the sum function itself is a sequential, and how do your scheduler know to split them into multiple jobs?
It doesn't. You have to do that up front.
Okay.
It doesn't know that.
Yeah.
That is part of the design of this system, is that each of these logical computes would be more or less self-contained. And if it needs to parallelize inside it, that's okay. But the outside system is not going to know anything about that.
Okay. So the coder still need to do the parallel way. Otherwise, if they write a sequential, one plus, the next plus the next, all the way, computer still cannot do it for you.
Absolutely.
Okay. Thanks.
No, the whole point was make one logical compute operation, which is simulate. What happens inside that simulate, the computer programmer doesn't know anything about. That's the data scientist's job. And if they want to parallelize it or do whatever they want to, that's fine. But logically, they're going to make one compute operation, and that's what's going to get scaled by AKS and by the durable function.
Yeah.
But that kind of goes back to what we talked about at the beginning. In the most ideal sense, to get the maximum operations possible, they would do exactly what you're saying. They would go in here and start optimizing and start pulling some of this stuff out, maybe into C++ or C#.
Yeah.
But they didn't want to do that. This was a monolith. They had spent a lot of time and effort on this, and they really didn't want to break this part up. They wanted to treat this operation as one logical compute and then scale from there. But yes, to get the maximum scale possible, they'd have to go in here and start optimizing.
But do we at least have some insights about the resource utilization? For example, if this code was not written in a very efficient parallel way, right? Then it would not be able to probably take advantage of a high-end, high-SKU, multi-core VM. And so if we see that, okay, that's the case, we're throwing an expensive compute node in there, and it's really not barely being utilized. And we'll simply choose a single core, for example, SKU for that purpose, and vice versa. Would that be a consideration, like one of the approaches to tackle this type of issue?
Absolutely. So you would have to put in additional instrumentation into this, and you might even have to kind of pull that out of Azure and do that instrumentation locally on your machine where you have multiple cores and you can see whether you're effectively utilizing it or not. But yeah, you would have to do that additional instrumentation to figure out that you're not effectively using all the cores.
But it seems to me that they are building Spark. It's their homemade Spark here. Databricks would do all of this for them automatically, would it not?
That I don't know. I'm not familiar with Databricks, and so I don't know if that would have been a different approach. Maybe it would have been. This was the approach that we chose.
Understood,
but maybe it would have. Absolutely.
No, it's a great architecture, don't get me wrong. But from the point of scalability and parallel processing, Spark-based computes would do a far better job than doing it yourself, because as Mike's pointing out, you're still not taking advantage of multi-core capabilities here. And this is a brute force approach, and 9 times out of 10 it works, no question. My question was something different, which is my lack of knowledge about Kubernetes. I thought horizontal pod scaler was designed for scalability. It looks to me that you're saying it is too primitive to scale according to their more sophisticated requirements, and that's why you went to KEDA, right?
Yes. So the horizontal autoscaler that's built into Kubernetes only knows about Kubernetes. So it can only monitor things that are running inside the cluster.
Yes.
And so it can only see how much CPU utilization or how much RAM a given pod is utilizing. That's all it can know. It doesn't have any external knowledge.
No.
But since we're building this in Azure, we know there's some external knowledge that we could inject into the process.
And that's the value proposition of AKS over plain vanilla Kubernetes, that it is wired to interface with KEDA and things like that? No?
No, KEDA is an open source project you can install on any Kubernetes cluster.
Oh, okay.
So KEDA is nothing to do with Microsoft specific technology. I mean, Microsoft is a contributor to the KEDA project, but it's part of the Cloud Native Foundation.
Right.
And it can run in any cluster you've got.
Oh, okay.
Now, KEDA is the default scaler that Container Apps is going to provide out of the box. But as far as Kubernetes is concerned, you can run KEDA anywhere in AKS or in any other Kubernetes environment you've got. It runs as just another service inside Kubernetes.
Got it. Thank you.
All right, so we have one logical compute. So we need to write that wrapper. So the wrapper is going to deal with interacting with Azure. So we can look at what this code will do. This code is very, very simple. Takes some environment variables that tell it what storage queue to listen to, where do I write my input data, where do I write my output data. And then it starts looping, saying, hey, give me some messages off the queue. And this is where we could have injected the batch. So received messages by default will take one message, but you can take up to 32 messages off the queue with this SDK, because this is the Azure SDK for Python. So if you wanted to write it such that it pulled 32 items off the queue all at once, that would be totally fine. In their case, they really wanted to keep it simple and let each one be completely independent, especially in case it crashed. And that way it would scale completely independently and it wouldn't hold on to 32 messages until it was done or it realized that it wasn't going to finish them. Because each time you take a message off the queue, you've got to call delete message to say to the storage queue, hey, I'm done with message 1. I'm done with message 2. I'm done with message 3. If you fail to do this, Azure Storage Queue is going to assume your compute crashed, and it's going to put that message back on the queue, hoping somebody else takes it. So it's durable. So you receive messages, you loop through those messages, one or many, and you delete them one by one off the queue to tell it, hey, I'm done with job 1, I'm done with job 2, and so on. This is where my compute engine gets called. So again, the data scientist only needs to write a function that meets this requirement, that it can take an input array or a NumPy array or whatever is appropriate. And they don't need to know anything about how this happens. And I, as the developer, only have to know I'm going to call into their compute engine, I'm going to pass in some input data, I'm going to process those JSON files so that it fits inside the algorithm the data scientist told me. I don't have to know anything about how it actually works. So this makes it so you have a team of data scientists who are focused on their job and a team of developers that are focused on their job, and they don't necessarily have to know the intimate details of what each other are doing. And that's it. This is the wrapper. It's really simple. It's really easy. It does just a few things. It's very simple. It scales really, really well because it's very simple, very logical, does just one thing. And that's what we want to get the maximum scalability, is to make it as simple as humanly possible. Okay. So now we can look at the autoscaler. The autoscaler is a Kubernetes object like we saw before. It's going to scale my deployment. My deployment is one or more pods, which have my compute engine running in them. And I'm going to give it a polling interval, a cooldown, minimum number, maximum number. And what is that external thing that is going to tell me the number of operations that I need to perform and how I need to scale? We tell it, hey, there's an Azure storage queue out there. This is how big I want that queue to be before you start scaling. And here's the connection information to actually log into it.
And this is KEDA, right?
Yes, this is KEDA. Yep,
okay.
This is why it can run in any Kubernetes cluster. It has nothing to do with AKS.
Got it. Thank you.
This can run anywhere you want to run it.
You have answered my questions. I just don't know how to turn this thing off, so my hand shows first. Sorry about that.
Oh, that's all right. And then here, this is where I pass in for my deployment. I want to pull every 5 seconds, cooldown of 30 seconds, 0 minimum, 100 maximum, target length of queue 5. And now I can do my deployment to any any Kubernetes cluster I want to.
Mm-hmm.
That's the Kubernetes side. That's the compute side. Now let's look at the Azure Durable Functions side. So Azure Durable Functions use the Azure Function SDK. So I have a durable function orchestrator. So this is really, really simple. All it's going to do is take the number of input items that I told it to do and generate some input data. I know, it's really, really complicated.
Hey, Jordan, real quick recap in case some folks aren't quite sure what a durable function is. Just a quick.
Thank you. Certainly. Let's go back and review that one more time to make sure. So durable functions are Azure functions, but that maintain state. So the whole idea of Azure functions originally was they're serverless. They're a Lambda function. You pass some data in, it processes it, and you get some data out on the other side. And it can scale infinitely. You don't care about the server it runs on. It scales as big or as small as you want it to go, and you're only billed for the compute as it runs. But what Azure developers realized is that people were constantly rebuilding these orchestrator engines that would maintain state to know I generated 100 input Azure functions. 3 of them failed because compute failed. I need to restart those 3. I need to wait until they're all done, and then I'm going to go analyze the results. People kept doing that pattern over and over again. And Azure Durable Functions does that all by itself. You don't have to write any of that code yourself. That's what durable functions give you. The durable functions, I'm going to generate some input data. I know, really, really complicated here. My sum function sums 1 + 1, you know, it's exciting. And now I'm going to start generating some tasks. Tasks are how you tell it to fan out. So I want to fan out and call this compute function. And here's the input data for job 1, job 2, job 3. And additionally, I want to wait for an external event. I want this compute complete function to occur. I don't know how it occurs. I don't care how it occurs, but I need to wait for it to occur so that I know I'm done with input number 1, done with number input 2, done with input number 3. And then I can sit there and wait for it to finish. So I don't have to write a lot of code to get that fan out, that wait, and then the complete. Azure Durable Functions already has an SDK for doing that. My compute function in Azure Durable Functions is really, really simple. So each time it fans out, it's going to run this little function. And all it does is connect to my queue, connect to blob storage, generate an input JSON file, write that data out, and then put a message on the queue saying, hey, now there's a thing called job 1 to process. Hey, now there's a thing called job 2 to process. And here's the path to that file in blob storage for it to process. That's it. Compute complete is really, really simple. It just needs to report back to the orchestrator saying, hey, I'm done with number 1. I'm done with number 2. I'm done with number 3. There's very, very little code here. Almost all of it is just a few SDK functions. There's almost no logic I had to write myself. This is stereotypical out-of-the-box durable function. I don't have to come up with this myself. And that's the magic. That's the greatness of durable functions, is that it's already there for you. This pattern already exists. I just have to call into it. Okay, so let's run it one more time now that we kind of know what's going on and what's going to happen. So I'm going to call the orchestrator. I want you to generate 100 input data. Okay, so to do that, I need to look in Azure. So let's look and see what's going to happen. Okay, so if we go and look at my durable function resource group, I've got an AKS cluster, got a registry, and I've got some storage accounts where I can read and write my input data. My storage account has an input directory, an output directory. My input directory is where I'm going to write data that needs to be processed. My output directory is where the results will come once they're done. And likewise, there's a queue where I can write the data I want processed. There's nothing on the queue right now. I haven't started it yet. But this is to show you the infrastructure that's sitting behind this general compute engine. Now I can start it. Azure Durable Functions is going to start. And you can see there's all these different methods already available that you could expose in your front-end application that would let you see what is the status of the job. It's pending. There's 100 input items. I started at this time. If we look in Azure, we can start to see messages are going to start showing up on this input queue as the functions start to scale out. There they are. So there's my input data. There's job number 1. It's tied to this, and here's the path to the data with JSON file number 1. And if we go look in the input storage container, we can see that now I've got some input data to process. There's nothing magical about these JSON documents. They're whatever input data makes sense. In my customer's case, it was multiple megabytes, if not gigabytes of input arrays. In my case, it's pretty simple. And then, of course, as Azure Functions continues to run, it'll start to write output data. And we can see that it does my super secret, really expensive algorithm that's going to make the company lots of money. It sums up the array. I know, it's exciting.
Jordan, on that note, we have a question in the chat. Is your super secret algorithm and code going to be available after this call?
Yes, absolutely. Feel free to take a screenshot. But yes, all of this is available on GitHub. Feel free to steal it and build on top of it. It's all available. There's nothing secret or proprietary in what I'm demonstrating for you today.
And we'll get that link posted to the Q&A of the meetup.
Is there a reason that you wrote the wrappers, the queue logic yourself in code instead of using the Azure's built-in trigger binding, for example? That would, take care of all the batching and the retry logic and stuff.
So again, the way we ended up doing it was we wanted these containers to be very self-contained. And so we just used the Azure SDK to do it. But yes, absolutely, you're right. This could have set up the bindings. to listen to Azure Event Grid. That's true. You could have done it that way too. We didn't do that. It's just a while loop that polls. But yes, you're right. That would have been another way to do it. Okay. As I said, all of this code is freely available on GitHub. We'll send you the slides afterwards. There's nothing secret or proprietary here. You can feel free to borrow the code, build on top of it. It uses standard Azure services. It uses Azure Durable Functions. It uses Kubernetes. It uses storage queues, and it uses KEDA for its scaling. And all of these services are available. You can get them. And we will send out the presentation on all the code afterwards. Are there any other questions or anything I can show you?
Yeah. Does this provide a log, show you how this part balanced? You know, we can see, you know, not some part very busy, some part, you know, very idle.
That's a good question. There probably are logs in AKS that would tell you that. I don't know them off the top of my head, but I'll bet you there are logs inside Kubernetes, especially if you installed like Prometheus and Grafana, where you could probably see that.
Or even container insights, which would also give you that, I suspect.
Okay.
But yeah, it's just a Kubernetes cluster. And so there very likely are things that would tell you that. And maybe Azure Monitor could even tell you some of that information.
Yeah, you'd want to install container insights, which is a feature of Azure Monitor, which would then surface up some of that additional data. If it's in there, you'd be able to see it through that.
Yeah, because sometimes the job log can tell you how good your code algorithm, you know, balanced, so you can adjust through the log. Thanks.
Right. And so this is one of the keys to saving money, is to have multiple node pools in Kubernetes. So Kubernetes has to have a few VMs running underneath it to run the services that make Kubernetes possible, like the scalers, like the deployment engines, all the things that make Kubernetes possible. You've got to have a few VMs to do that. And so that's what you see here with this agent pool, and it runs on really cheap standard DS2 v2 VMs. But for this data science workload, they knew what SKU they wanted. In this case, this wasn't the SKU they picked, but they wanted one with a lot of CPU, a lot of RAM, a GPU available for it. They were very picky in what they wanted their Python scorer to run on because they knew that's what it needed to run. And so you make a separate node pool that runs the really expensive compute, and you let that scale all the way down to 0 when there's nothing to do. But you've got to keep this other agent pool running, but it can run on very cheap VMs that don't burn a lot of money. But the problem, of course, with node pools is they're built on top of VM scale sets. And so they don't scale as fast as you would get otherwise. And so that's why you use KEDA to scale up the... I'm sorry?
Do we have any, and on that comment you just said about, you know, scaling performance basically, and algorithm, do you have any comments on how well this KEDA thing works compared to, say, Microsoft's algorithm to scale up Azure Function Consumption Plan and app service, the ones that Microsoft uses behind the scenes to make all that other past scaling works?
That I don't have, no. I don't have that information.
Fair enough. That's most likely. I would assume Microsoft must have used some kind of proprietary stuff, you know, based on their own optimization. Probably lots of those.
Right. Very likely.
This is a question on the side. Somebody brought up the whole instrumentation and monitoring and performance tuning, container inspection. Is there a feel how much that impacts the performance of the cluster when you're trying to grab all the data? Is it 5%? Is it nominal?
Theoretically, it shouldn't really, you shouldn't notice it. KEDA was very much written to run in Kubernetes and run on these kind of bog standard, what is the right word? Management nodes, which are always going to be small and simple.
I can see how KEDA would be a small footprint. I'm talking about when you go to try to analyze, oh, are we using 2 cores or 4? All the instrumentation you add to kind of inspect the performance, not manage the scaling. Scaling makes sense to me.
Gotcha. I don't know. I don't know what kind of performance hit that would put on it, but there was a joke that I heard at Oracle's conference a long time ago. So the Oracle database is heavily instrumented, And somebody asked Tom Kite, who's a very famous developer on Oracle. They said, "Hey, Tom, God, there's a lot of logging going on in the Oracle database. Wouldn't Oracle be a lot faster if you just got rid of all that logging?" And he went, "Well, I think if they got rid of all the logging, the Oracle database would be negative 10% faster than it is today. Because if you can't measure, you can't improve." And so, yes, there is a performance tax associated with all the monitoring in any given system, but that tax is worth it because you can't figure out where your performance bottlenecks are if you can't measure them. If you just look at some code, you can't really in your head guess where the performance problem is. You're always going to be wrong. It's the whole idea of premature optimization is the root of all evil. I think that was Donald Knuth, right? I think he's the one who said that. Might have been von Neumann. But anyway, if you don't measure, you're not going to be able to figure out what the performance problems are. You're not going to be able to make your system fast. And so it's worth it to pay that tax to monitor what you're doing. Now, of course, you have to balance that and you have to decide what's right for you. But don't be scared of the monitoring. The monitoring is your friend.
No, AWR reports are my friend at times in Oracle. So
put a link into Container Insights for folks that want to understand that a little more. So there is going to be an overhead to this, I'd say, like Jordan was saying, but there's going to be basically some minimum requirements you're going to need on your node sizes, but I don't think we document that in terms of like what it will need, because it's one of those questions I think that the answer to which is it depends.
Okay, any other questions or anything else I can show you?
One quick question. Okay, sometimes if people, let's say 2 people or 3 people submit a big job at the same time, the one of them may grab the resources, don't release it, the others couldn't do anything. Right. Can you assign the job priority as an administrator so make sure the system still work?
That's a good question. Let's think. What would you have to do? I don't know.
Maybe you could taint the deployment so that you've got different node pools, perhaps.
That's fair, right?
So but whatever the workload of the container is, you would have a node pool that's designed that's picked for that. Have different node pools for different jobs. Deploy the containers to that via tainting it, and then everything else.
You can tag the job. You can tag the job to label priority, for example, in the queue itself. And when orchestrator sees that this message right here carries a priority of 1, it might maybe choose a specific pool like Adam just said.
Mm-hmm. Yep. Yeah, I think you'd have to build that yourself, or like Adam said, you'd put in some taints to say go to one pool or the other pool.
Yeah.
Okay.
So the container workload would only run on a particular pool, and so scale out and in and out based upon that particular container workload. Mm-hmm. That might solve it.
And this customer, let's say, have they, for example, tried, let's say, Azure Function Premium? Would that just still doesn't offer nearly enough the horsepower they need? But let's say, Azure Function Premium does release a SKU today that has 10 cores and with a GPU and like that, and this entire thing could have been avoided and just let Azure Function do its thing. Is that take?
Let me think. I don't remember if they ever asked me that. Let me think. What did we talk about?
Still have the Azure Function limit of a 10-minute runtime.
Oh, you're right. That's true. You would exceed the timeout limits of Azure Functions if you couldn't get enough. That's fair. Yeah, that may have been why we didn't go down that path, is we knew a lot of these jobs would exceed that timeout based on how much input data we were seeing. I believe that's right.
Default's 5 minutes. The max you can go is 10 minutes, and then your job is killed. So if your code isn't done in that, even if you've maxed out the horsepower of the underlying app service plan, you're done. So that's why more horsepower from Kubernetes nodes like this would be a good solution for that.
That's a consumption plan, isn't it? Does a premium plan have the 10-minute as well? I forgot.
It's a good question. Let's find out.
I I'm going to say yes, they do, and be prepared to be wrong.
Yeah, it changes every day.
It says
entirely possible
unlimited
yesterday
execution
it was,
duration
and-
with 60 minutes guaranteed. It does actually has.
All right, so it'll give you some more. Won't give you infinite, but it will give you more.
But it only offers 1 core, 2 core, and 4 core instances. So this customer, if they're probably specific, they want something that's way more powerful, especially that GPU side. I don't think that's offered on any of the function SKUs.
Yeah. I mean, ultimately, Azure changes every day, and tomorrow it might have something that would have fit perfectly. But at the time we built this last year, what they wanted wouldn't fit in any option that we had available.
It was down a bit underneath cold start behavior, the runtime, the service limits, default, max timeout duration in minutes.
There we go. Very good.
Okay, can we study? All right, today I learned. Excellent.
Yep.
Good. Another day not wasted.
Okay. Anything else that I can show you or you want to talk through? No? Okay, well, thank you so much for your attention. I really appreciate it. And like Adam said, all the code and the PowerPoint and everything will be made available after we get done today.
Yeah, we'll put many thanks, Jordan. Really appreciate that. I can close us out. Yeah, we'll check the Q&A. We'll for the Meetup page that we have, we'll put links to the decks and stuff that Jordan had up there. So many thanks to Jordan once again. Third time. We'll let you take a break now, Jordan. You can have some rest. We'll give some other speakers.
I got to build some other cool stuff.
Indeed, there you go, and then we can have you back. So thanks everyone for joining us today. Really appreciate everyone joining in and the great questions and Q&A. Next month, we actually have planned Azure Arc, Azure Arc, an overview of what that is and why anyone would care. So I haven't got the date figured out yet, but that's the topic. The speaker has volunteered. Need to nail down a time sometime that works for us all in April. It might be in person. I'm not going to promise anything.
That's what we want. That's what we want.
Right. That's what we all want. So the Microsoft Office is releasing a lot of restrictions on April the 4th. So it might be in person, and that will be. So we'll see. We'll see. That's the hope. I'm not going to guarantee anything because I've said that so many times. So that's the topic. Might be in person. Really hoping it is. Hope to see you all here. Thanks everyone once again for joining, and hope to see you next time. Take care, everyone.
Thanks a lot. Take care. Bye.
Thanks all.